welcome. My name is Katya, and I'm really thrilled to welcome you guys here to our first quantum programming webinar. The idea is to make these webinars monthly. They will live on our YouTube page, where you could also find my podcast that I run with my 9-year-old son. And the idea behind both of these things is to educate people about quantum computing, because I think one thing that is really lacking right now is quantum workforce, quantum talent. The hardware is getting there, the software is getting there, but we need people who will actually write the algorithms and program the quantum computer. So we need you guys to actually be able to operate these machines. So it's really great that people have been very responsive and are joining us here today. And we also have a super great presenter with me today, Robert Loredo, my former colleague from IBM. I'm just going to say a few words. Robert, I don't want to make you blush or anything, but I will say a few nice words about you. So Robert's been in the quantum business for a while and worked at IBM for over 20 years. Holds a whole bunch of patents, actually 270 to be precise, which is amazing. And at IBM, he changed various roles, and every role was ever more important than the other one. And just before he left a few months ago, he was actually the global head of IBM Quantum Ambassador Program, which is a super important program. I was also part of it. And that's when people are able to actually talk to customers and other people outside of IBM about quantum. So super important to get everyone out there up to speed with this emerging technology. And right now, Robert has started his own company, Entangled Solutions Group, where he advises and educates industry leaders and startups about the potential impact of quantum computing. He's done a lot of these webinars, seminars, lectures, virtual and in person before. So you're in really good hands. And by the way, he also wrote a book, which I ordered. It hasn't arrived yet. Otherwise, I would have showed it to you guys. But I'm really looking forward. And with that, I'm going to pass it over to you, Robert, if you want to add anything to this introduction and maybe tell us a little bit more how you started in quantum and why we should even use quantum over classical computing for optimization, something that we're going to be talking about today.
Sure, great. Thank you, Katya. That's fantastic. So it really kind of started off with, at IBM, they launched their first quantum system out into the cloud for everyone to use back in 2016. And most people that joined, it was kind of a launch where mostly were physicists that understood what quantum was and thought, well, that's interesting to use it. When I first heard of it, I went to the page that we had back then, and it was really just a pamphlet, a user guide on how to use it. It was not all this massive information and education content. And the guide pretty much started very simple at first. What is a qubit, zeros and ones, and these sort of things. It made sense, small matrices and everything. And then page 2 jumped right into Hamiltonians and observables and things that, was pretty much written for physicists. So it had a very steep learning curve, basically. So thankfully, as we developed and as, of course, the ecosystem itself grew, folks like yourselves that have interest in it, understand it, or want to understand it, and thought up very, very, very fantastic ways of describing it and programming on it, etc. So much that there are now high school students that I've gone to and done seminars with, and many of them have already started using quantum. It's really good to see that even younger, talking about it, the Quantum Kid, for example, has his own channel now. So there's a lot of activity and learning since then. Right now, you can find information everywhere besides books. There's obviously, of course, Qiskit community being the largest ones. You can find lots of information there on their YouTube channels as well as tutorials. And I started by just getting interested in it. It was actually my mentor, which I highly suggest everyone have. I was in AI at the moment working with the Watson team, and he said, hey, if you're interested in quantum, I know you talked about research and stuff in the past, and this might be an interesting area. And then they started the ambassador program. I started off as one of the first ambassadors that got in around 2018. Moved my way up towards leading the program, which I've done for the past 4 or 5 years now. So it's been great. It's been fun, of course, because you get the opportunity to inform and educate people on quantum, but also hearing some of their ideas. I mean, people, once they get a grasp of the concept, the difference between classical and quantum, they really, really have a good sense of creativity and come up with some very interesting projects. I've seen people come up with games. They came up with apps on phones on how to learn about gates. So for today, one of the things I wanted to do was just kind of bring you all in on one of the more promising areas in quantum. To kind of help you not only get started, but kind of springboard you up to somewhere towards like an intermediate level. The tutorials page is pretty much the one place I generally tell people to go in the first. But they have a whole getting started section. So for those of you that are brand new to quantum, this getting started section will really help you get up and going. Just installing Qiskit and getting connected, creating an API key with the platform so you have access to the actual quantum computer so you can start programming those. Then the next section, once you get all started, you to share this sort of hello world type of a program to run, just basically something you can run on a simulator and then run the same program on an actual quantum device. That pretty much just gets you up and running. You created a circuit, you ran it, you transpiled it, you executed it on a system, and you do some post-processing, whether it's a display a word or it's display a graph, it'll get you started. If you really want to go a little bit more in depth, then there's a whole section on workflows towards Advantage. What that basically means is, how do you create a particular workflow, some experiment or a real world problem, solution to it that leverages quantum computers? How do you pretty much blend that into your workflow, meaning into your classical system? Right now, everything is classical, and just for awareness, we're not going to move everything from classical to quantum. Your data is still classical. Your data repositories, your data streams. So there's no need to change that. And your applications are classical, right? But now within that application, if there's some programming or some computation you need to do that's very difficult or not quite possible on a classical system, then perhaps a quantum can solve this problem. So how do you then, within your workflow, offload that computation onto a quantum system, get its results back, and then keep going through with your application? So that's what this workflow towards Advantage means. So Advantage, in a sense, is to say, well, I want to come up with a particular problem that I can show some potentials now with these current systems, but I also have a way to increase that or evolve that particular solution. So as the systems evolve, so does this solution. And eventually when we get to a particular size or we're able to attack a problem that's difficult for classic, but it works very well with a quantum computer, then that's when you can sort of, in a sense, say, look, we have some quantum advantage here, which is just to say there's advantage using quantum over classical. The last part is on Qiskit capabilities. So what capabilities does Qiskit have with respect to creating a quantum algorithm? How can it make you a programmer, whether you're a quantum application developer or whether you're a quantum computational scientist? There's a lot of capabilities that are built across the board. As you can see, the different types of problems. The one we're going to be working on in this particular session is one of these QAOA or quantum approximate optimization algorithms. These are the types of problems that we see that as quantum having a potential. It's chemistry, optimization, and then even machine learning. What is an optimization algorithms? Basically looking for the best solution from a set of possible solutions. For example, if I say we want to drive from New York to California, and I ask each one of you, hey, what's the best way to get there? I'm going to hear different answers. I'm going to say, well, the best way, we could just take a flight. Or someone say, no, let's take a road trip. We can make some multiple stops. And others say, no, let's just take the highway. Lots of options. But what's the best? If we can take our time and enjoy the trip, or if it's just, we want to deliver something, and what's the best route to get us there? This is the type of algorithms that we call optimization algorithms. So how can you optimize your particular solution to the particular task at hand? Let's get into programming. So Qiskit patterns, right? It's a general framework for breaking down domain-specific problems and contextualizing those capabilities in stages. So simply termed, is we're breaking down everything that runs on a quantum computer from the input to the output. We're breaking that down into particular stages so that it's easier for us to know where we're programming. Because you can then determine, well, am I going to be doing all the programming across the board, or can I leverage some existing libraries and tools so that I'm only focused in the area that I'm really looking at? So there's actually 4 steps to it. One is mapping, and this basically is how do you map your problem to a quantum circuit and operators, meaning how do I get my classical data into a quantum state so that I can create a quantum algorithm that will run on a quantum computer. If you want to be able to map this particular problem, I have this data, I want to offload it to a quantum computer, how do I do that? Second one is optimize, right? So now that I have a circuit, because the mapping will create this circuit and a whole bunch of operators that will operate on all of these qubits, so how do I optimize this? Meaning as soon as I have the circuit on the digital frame, meaning the circuit that I drew up, it's to say it's 4 qubits, then I have some connections in between, so I'm entangling some, I'm running some multi-qubit gates on there. Now, I'm going to put it on a hardware to actually run on the actual circuit board that's sitting on the quantum computer. But that circuit board has qubits, but they're mapped in different ways. Each qubit's connected to 2 or 3 or more qubits, and then each one is connected in a sort of some kind of configuration. So how do you best optimize? Where should qubit 0 go on this particular circuit? Should it be qubit 0 or should it be qubit 1? So it looks for this optimization does is it looks for the best qubits, ideally. You can either say, put it exactly where I map it here, because this is how I want to run it, or you can say, optimize it as best as you can. Find the best qubits with the best coherence time, the best gate fidelities, the one with the best connections between the qubits, because if I'm entangling, I want to make sure that there's no errors coming in between or no noise being introduced. These quantum systems, they calibrate every day practically, and then they make sure that those numbers are known, so that when this transpiler, which will basically optimize this, will basically do that and do that well. We also have AI enhanced transpilers built in, so you can go in there and AI will look for patterns. Next one is execute. So if I want to execute on this hardware, how do I run it? So there's a runtime on there, which is basically the software that sits right alongside the computer. So there's primitives. You have two types, an estimator and you have a sampler. Sampler just says, here, run this X number of times, number of shots, which means how many times you want to run it across the circuit, and give me the results. Count each time what the results are, tally it up, give me the results, and I'm done. Estimator is a little bit different because it's going to be running that same circuit, that same control multiple times. The difference is it's going to have some parameters, meaning over here, my gates are adjusted at a certain position, so it's going to run in that position and it's going to stay there and it's set. Over here, I'm going to be able to adjust my parameters, and I can tweak things as I get back the results. And the way I tweak it is going to be towards some function, right? In this case, for the optimization, is going to be a cost function. The easiest scenario to think of this is, if you think about your car, when you turn your car on, you're just going to turn on, it's going to run, and it revs up, and all the controls come on, and it's set. But if I'm listening to the radio in my car, and I want to adjust the bass or the treble or the speakers, those are parameters. That's the difference between the sampler and estimator. Sampler is just set functions. Runtime has parameters that you can adjust. And we'll be using the estimator here. And finally, of course, post-process. When I get my results, what can I do with it? Do I want to visualize the results? So here, for example, we're going to be focusing on the mapping. Just getting a problem, finding an ideal problem, and then we're going to use the out-of-box transpiler execution, and post-process will be just viewing the results and then iterating on our results based on what it is. Now, QAOA is an algorithm using quantum information to be able to optimize a result, to at least get an approximation for it. One of the most studied problems is what we call the maximum cut, or max cut as it's known for short. It is what's often referred to in complexity terms as an NP-hard problem, meaning that as you have more nodes here, for example, or vertices, the problem starts to explode as far as computationally, meaning with a small scale like this, a system can pretty much solve this problem. But as we start adding more nodes and it gets very complicated, then this problem becomes very complex and difficult for classical algorithms to be able to solve efficiently. When this expands, a good example of some other problems like this is like traveling salesman, where it has a lot of nodes and requires some kind of computation. Each edge will have a weight to it. You can see here it's 3, 4, 2, 5, etc. And then basically the idea is, what is the best way to cut this so you have the most optimal values on each end, right? So we'll be creating a graph, and ultimately what we're going to do is we're going to be mapping a problem. So it shows you pretty much how to do that here. It shows you how do you formulate it using a Hamiltonian for that particular problem, and how do you build that particular problem out using these poly gates, poly lists, right? Well, polys are just basically that. They're operators that you use to set for a particular component here. So you can see how they're described in detail here, the output. But ultimately what that mapping will do is create this particular circuit. You're going to have a few heteromers, which means you're going to put every qubit in superposition, and then you run some operations. Here we're basically running multiple operations, and the parameters here, as you could see, are by these two values, gamma and beta. If you want to think of it from just an analogy perspective, think of that as bass and treble, right? If you're thinking about this is a sound clip we're trying to optimize. We want to optimize the best sound for this particular type thing. So how much bass or how much treble. So you adjust this for each one. And then of course you could repeat it as many times as you need it, depending on your algorithm and what you're looking for in order to resolve these. Then what that'll do is it'll create that first parameterized circuit. You can see this is the red area here. And of course, then you need your measurements. Then the next step is to optimize the problem. And finally, when you execute it on the quantum computer, there's different ways you could do different execution modes. A single job means just a one-off. So once your job comes in, it'll run it once and then give you a result, and it's done. Then there's something called a batch, which is new, which is basically a precompiled maximum set of jobs. I mean, I want to run this 3 and only 3 times, and here's how I want to do it. I want to batch these together. So it'll run them together, and the one we'll be using here, because we're going to have multiple iterations, will be sessions. A session means you're dedicating the entire system, and then that whole part, when your job comes in, it'll be the only job running, and it's going to basically execute one. It's going to check the parameters, make an adjustment, run it again, but with the new parameters, listen to the output. If it says okay, it'll run it again. It'll keep going until it's done, or until you reach that cost function, a minimum value, which means that you reach that the critical point that you realize, okay, we've reached our goal. So there's different types of optimization problems. There's linear programming, and that's where you think of it as what your objective is. In this case, let's say it's selling, like in the example we have here, we're trying to sell a product. And then there are constraints. Well, you can only sell at this particular price, right? So if we want to maximize profit and then we have a fixed price, then those are our particular objectives and constraints. Integer programming means you can't break it down. And then, of course, combinatorial problems. As an example, is we're going to have students and we're going to break them up into 2 teams to have a debate. But we want to make sure that when we break them up, that the friend connections there are there, so they can have a nice, good debate between them. Now, the max cut problem, as you saw from the image, is basically a lot of nodes, and then there's connections in between edges. Think about them, each node as a student, and we want to divide them into 2 groups, with a maximum number of friendships that cross between the groups, meaning these folks are friends are on opposite sides in a sense, so they can have a nice healthy debate and not be annoyed by each other. Here, the problem set you can see here, we're given a graph, so we're going to have a graph with weighted edges, and which is the friendship between the 2 of them. And of course, the vertices will be the students themselves. And we want to put them in 2 groups where we pretty much come in across. Now, this is considered an NP hard problem because small, like 5, we can solve, which is what we'll do here. But when you get a class of 30, you can see that there are over 500 million possible ways to split them, right? So as you increase these numbers, this problem gets larger and larger and larger. It becomes very difficult or just time-consuming for classical systems. So how do we solve these kind of problems? So you could use a greedy method, which is to start with a random partition, move them into different areas. Then there's a randomized algorithm, which basically randomly splits them and says, okay, this is it. And this surprisingly gives you about a 50% optimal on average. But we're greedy, you're putting things around and you're moving things around as you change values. And then, of course, semi-definite programming, right? And it's been known to give you solutions within 87.8% of the optimal one. Cost functions. So basically they say how good a solution is, right? So you're looking for the best optimal solution here. So how do you determine it? Well, what's the cost? You look at it's either a maximum number or a minimum number, right? But how can you get to that particular one? So properties of a good cost function should obviously reflect your true objective. In this case, our objective is to maximize this number of students by their scores, by their friend scores within 2 groups. We got 6 students. With different friendships, weights, etc. So between friend A and B, the weight is 3. Between A and C, it's 1. Between B and D is 2. C and E is 4, etc., etc. Right? So if we try the greedy approach, we'll start with 2 groups. Let's just split them right down the middle and see what we get. So we put group 1 with A, B, C, and group 2 with D and E and F. Then here's pretty much what we have. Pretty much is drawn out. So we have the students, the friendship, and then this is more sense of the graph. There's a typo here. This D to F should have a 1 this way, not between D and E. Apologies here, but you could pretty much get the gist of what the connection and weights mean here. So we have 2 groups, and then we look at the combination. A to B, both are in group 1, so that doesn't cross. It's in a certain group, so that doesn't count. A and C are in the same group, that doesn't count. But B and D, or B is in group 1 and D is in group 2, so that does cross, so check. So the weight between B and D, we know, is 2. Between C and E, the same thing, they crosses, so check, we got that condition set, and then their value between friendship is 4. The other 2 don't cross, so the initial value here is 2 plus 4, which is 6. All right, that's fine. So now that's our initial setup. Now we want to apply a greedy improvement, so let's move one of them over. So we move A over. So now we have 2 groups, same 2 groups. So we now have B and C in group 1 and A, D, E, and F. Now we do apply the same rules here. Look at the weights between each of those that cross. And we can see here we have 3 plus 1 plus 2 plus 4, and that equals 10. And that's our solution there. Now, if we keep looking around, we'll probably find another solution, which we do. So we have our current group here where we moved A over. But if we move B over, we can see here that now we have A crossing C, B to C, etc., etc. So we can see that that does 5. However, by moving C over, we see that B does have a lot of connections with the others at high value. And pretty much when you add them all up, it becomes the same. It's the same value, 10. So there's 2, and you can, of course, try moving. You can see where all the different permutations can pretty start adding up. So you have to calculate everything one at a time. Of course, but we'll just stop here for now. For time purposes, and say, okay, our optimal partitions here are either having group 1 with B and C, and group 2 with A, D, and F, which is the cut value of 10, which is basically the first group that we found. Because if you're running an algorithm, it'll find that, it'll be done. So our crossing edges here are just what we saw here from group 1 to group 2 of that solution. We have an idea. That's pretty much an example as to what max cut sort of is. You could put them in partitions, do some weights, shift things around, see what the totals are, and keep doing that until you find an optimal solution. And when you do, which in this case, the higher the number, the better, so it's a max, then you're done, right? So if you want to compute something like this, now we want to do this using a quantum computer. So you have Qiskit version 2.1, Qiskit Air 0.17.2, and the runtime of 0.40.1. So if you run this particular one, it'll give you the same output. It'll show you exactly which versions you have. If it's not working, then check to make sure that at least the versions that you're installed are the same. If they're a little different, then you could just uncheck any one of these three. So this is the version that I use for Qiskit, for the runtime, and for the Air, which is a simulator. You could just uncomment that and then run this, install it, restart your kernel. So that way you can at least have the same version that I have installed. Then when you're done, of course, you can reinstall the version that you had previously. Then you run this circuit, which just installs some libraries that we need, like the pass managers. That's for transpilation, for circuit, things for that we're going to need in order to create the graph, all of these sort of components. So here, of course, generating the graph, and what we're doing here is just creating that. We're creating that connection between the students that we had earlier, right? So here we're just using 5 rather than 6, just to make it just to kind of follow along with the graph. So you can see between 0 and 1, and of course we're just going to make them all the same, just to kind of make it simple as well. So you can see what you're getting here is a connection. So from node 0 to node 1, node 0 to node 2, and node 0 to node 4. That's what you see here in this graph, 0 to 1, 0 to 2, and 0 to 4. And then the weight, meaning the weight of these particular edges are 1. They're all the same. But if we want to follow the same one as a student, you can, of course, change this 3.0, 2.0, 4.0, whatever the values were that we saw earlier. And, of course, you can increase the size to the same size that we used. So then, of course, you're going to add the edge list to create the edges in the graph, and then to grab the node and everything you can display here, pretty much what we just drawn up, which is very similar to what we saw earlier. Now, so that's our problem. So now we want to map this problem. And to do that, we want to be able to maximize those particular connections. And what you've done here is you want to be able to get that graph and turn it into this optimization problem. So how do we do this? One, I'll do this from backwards to reverse, so it's easier to understand here. So the binary variables first, right? So x underscore 0 all the way up to x underscore score. Those are our binary variables. Whenever you're defining optimization, you want your variables. These are the components that you have within your problem. No constraints. We didn't have any. And if we wanted to have them, we can, but we just don't in this particular case. And then we want to maximize these particular values, which is the solution that we're looking for, right? So it's the 2 times x0, x1. So these is pretty much the connection between the nodes. So 0 to 1, 0 to 2, 0 to 4. 1 to 2, 1 to 3, 3 to 4. So we're just it's basically drawing out in this form, in this quadratic method here, what we've drawn up here already. So it's grabbing that problem, and this is pretty much how we want to maximize those particular pieces, meaning we want to maximize those connections between those nodes. So this is how we create the Hamiltonian. So now that's from that perspective. So how do we do that? So the easiest way to describe it here. We're going to grab that particular graph, the list of the edges, right? We're going to breed each one of those in. We're going to apply the weight. We're going to grab the weight for those particular connections between the 0 and 1, 0 and 2, 0 to 3, 1 to 3, etc., etc. And then for the connections that do have a weight in between that are connected, we're going to append a z on that particular list, meaning that between this node and this node, we're going to put this. So z will in a sense be that same connection to say this node is connected to this node and everything else remains the same, which means they get an identity, meaning nothing will happen to that particular node. We want to identify those. So when we build max cut polys from this, we'll see this will come out. With Qiskit, most textbooks, when they write the order of qubits, you're reading it from right to left. So here, the very first Z you see, that's actually node 0. The second one is node 1, node 2, node 3, node 4. So here, what are we doing? Because we're putting the Z between those two nodes, that means between 0 and 1, there's a connection, right? Between 0 and 2, there's a connection. Between 0 and 4, there's a connection. And if you remember, 0, 1, 0, 2, 0, 4 are the connections from that one node, right? And here's the rest of the graph, which is from 1 to 2. Here's 2 to 3, and of course 3 to 4, which is what we saw in the graph. And each one of those has coefficients of 1, and this is just basically the weight, right? We could have adjusted these are the students. This would be 3, 4, etc., etc. So that's what we have here. So now we've mapped the problem in this sense, right? Now we want to create the circuit, and then this is simple. You just call it the QAOA ansatz, which is basically say, this is what we're starting from, and this will create the circuit. And of course, we're adding measurements because we do want to measure all of that afterwards. So here's the circuit that it created, the ansatz, and then here are all our measurements so we can measure. So now the circuit is done. So we've mapped our problem from a graph into a circuit, and now we can actually run this. So how do we optimize this? So there's a function called generate preset pass manager. It's a manager that manages all of these optimizers that we have. And I don't mean optimizer like in our function. I mean optimizer like optimizing the circuit. One pass could be, I'm going to find the best qubits that I have, and I'm going to rank them in order for you. Another one could say, I'm going to find the best list of qubits that are connected that has the minimum number of errors, and I'm going to rank that list for you, and I'm going to provide that to you. So all of these passes go out and look for the best way of doing something. I'm going to find the best way to connect two qubits. I'm going to find the best way to connect, to lay out these particular qubits on this particular processor. So the pass manager pretty much has all of that. And then you can tell the pass manager how stringent it should be by this optimization level. Optimization level run from 0 to 3. 0 meaning don't optimize it. If I say qubit 0 goes to qubit 0, you find qubit 0 on that processor and you map it there. If it's going to be connected to qubit 4 and qubit 4 is on the other side of the processor, I don't care. Let it put it on the other side to have it traverse all those gates to get them back. That's fine. That optimization means don't do anything, just do what I say, and that's it. And of course, the levels go higher, which means that how much more error mitigation, error suppression is attended, where optimization level equals 3 is the highest, meaning everything you can do the best of the best that you can. And here's the backend that we're going to use, and just map it to that particular hardware. And how we determine the hardware here is using the Qiskit runtime service. And basically what we're asking it to do is to say, give me the least busy system you have, because I don't want to wait in the queue too long. And I want to make sure that I'll make sure, and these are the parameters, make sure it's operational, make sure it's not a simulator, I want a real device, and I want to ensure the minimum number of qubits is X. In this case, it's 127. And I want that backend, right? So when I ran this, it was the Torino system. And then once I have that, then I have the backend, and I have my optimization level and my circuits. So I grab that particular pass manager for that particular backend at that level, and then I say, okay, I want you now to run this circuit and optimize it. And this is going to be my candidate circuit, right? And that's what you see down here. It's really small, but when you run it, you'll be able to zoom in or open it up to see the details. But basically, that circuit that you saw in those little Z's and I's, all that's going to get pretty much mapped into this particular one. And this is now optimized. You can see there's 5 qubits, and then 1 measurement down in the bottom. And that's out here where all the measurements are done at the far right. But all these you can see in here, those are all operators and gates and stuff that we have going on in order to be able to create that circuit, that problem that we've had. So now that we have this circuit, now we want to execute it. So we want to execute using the Qiskit primitives. Because we're going to be adjusting, remember we have that gamma and beta values we're going to have, remember the bass and the treble that we want to adjust, or the number of students we want to move around. So that will be a parameterized circuit, so we want to be able to use the estimator here in this case. So we want to estimate our observables. That's what those I's and Z's are. They're called observables. So we're going to define our values here. So if we're going to be using our initial parameters, so we have the gamma, the beta. We're putting some basic values here of rotations of pi for gamma, beta is pi over 4. That basically means how far am I rotating this particular gate. Pi means I'm basically facing 180 degrees the other way, and pi over 4 means I'm going a quarter of the way out there. Right? That's pretty much how you're defining it, and then you're initializing it here. So those are your initial parameters. Now that I have my parameters, I want to now run this. So first, let's define a function that will run it. So we're going to pass our parameters that we just defined, the ansatz, which is the circuit, our Hamiltonian, and the estimator, which is the particular primitive that we're going to run. So the Hamiltonian, we're going to apply this layout. That's pretty much going to say, okay, for this Hamiltonian circuit that I want to create, which is what we created there with the I's and Z's, this is the layout I want to have, which is that circuit we just created. And this is going to create this particular ISA, Hamiltonian. Then I'm going to say, okay, I want this to be the list of circuits. My estimation circuits are going to be this. So it's going to have a parameter, the circuit, the ansatz, which is the initial value that we're setting everything into, the circuit itself, and then the parameters that we're going to be running. And then now, after all of that, we have the backend, we have everything set. Now the estimator is going to now run that particular circuit. And when it runs, it's going to hold it into a job object. So now when I hit run, it's going to run on that particular piece. It's going to do its process, and it's going to give us back our results. And our results, we want to grab back the first one that comes back. We want to look at the evaluation of data so that we can evaluate those, right? That's going to be our cost, right? Okay, this is the result. Just similar to what we did when we were adding all those numbers. And then we're going to find, we define somewhere later here this objective function values, where we're just going to be, we're going to identify, okay, what is the, is this the best answer, right? So we're going to pass this into that, and it's going to keep a long list of track of that, and then it'll look for the most optimal one. That's all this function does. So if we're going to run it, for us to run it, we'll run it on a simulator. So we'll have to import the simulator here. The air sim will be what we'll call it, and then here's the objective function values, because there's going to be an array of values. Because we're going to run this a few times, and we want to compare and find the best one. So we're going to do that using this session. So this is the execution mode. Remember, there was a single job, a batch job, and then a session. We want a session. Why? Because we're going to do this a few times and iterate. So we want to make sure that it runs as many times as we need it in order to be complete and then give us back our results. Right, so then we can define other things within our different options. For now, we'll just define a number of shots, meaning how many times I want to run this circuit before they give us our results. This will be 2 to the 12. When we get done with that, we're going to call this minimize function. So this is a minimize function from the SciPy library. So if we want details, I provided a link to that as well. But basically from there, we're going to pass this cost function estimator, which is basically, as you saw earlier, what's going to run our program. So this is going to return the result of that, which is the cost. It's going to return the initial parameters. We'll pass in some arguments here. And then obviously the method that we want to use it to minimize is going to be this cobula. And then any other parameters you want to add, you put in there. But basically, this will give us our minimized results for that particular run of the component. And then we can obviously output that when it's completed. So after we run this is pretty much what you'll get back. You'll say, okay, it terminates successfully. You'll get back a success, all of that. And then, of course, you'll get your function result, and then, of course, the various different parameter values that were set for this, right? And then after this, you come down, you can graph it, you can visualize to see it. We've got some more. As we iterated more, we could see that we come much more towards our minimum as the things adjusted, and pretty much hit it pretty much a steady after around 35, 37, maybe going towards 40. We pretty much hit our plateau here. It doesn't seem like it's going to drop much more. So we can definitely say that we hit our minimum for this one. Then you can go ahead and assign the result from that one. Say, okay, now I want to adjust to that particular value, and I want to run it again. This time we want to run it on using the sampler, and you can run that as well. It gives you some more specific results from that particular piece. So you've executed both using both here, and obviously you can get different results from each one. It pretty much this one gives you the idea as to what parameter will give you that grounded state or better minimum in this aspect. And once you have that, then you can get your results back. And this one is just basically doing that. It's getting your results. It's going to say, okay, you ran this on the component. You ran these different distributions. So what does this look like? So for every different permutation, you can see here the bit strings. Of course, these are reversed. Remember, we're reading from right to left. So you can see here the results that we get back. You can map these however you like, but this here is a post-processing thing. This reality is more up to you. This is just one of the examples that they use in a tutorial to describe so you can see the results. But if you're running a particular application and bringing it back, this will show you pretty much how to do that. So this is just to visualize the best cut. It shows you here. It highlights the cuts here. So you can see it cut this one and this one out, which is in gray. The others are purple. And that is your result from this solution. I'll open up for questions now here.
Fantastic. Thank you so much, Robert. Yeah, we've got a question here from Alex. Is it possible to estimate how much this QAOA optimization is more or less efficient than classical optimization methods?
Yeah, so that's actually an interesting question. So there's a lot of research going on how to actually estimate the advancements or the advantage that quantum and classical have. Because when you break it down, there's different types of ways to solve a problem classically. There's brute force, which a good example I always use is if I want to count from 1 to 100. Brute force is I'm going to go 1 plus 2 is 3. 2 plus 3 is 5. You can do it step by step and iteratively. Or you can go through some numerical analysis or tensor networks or some other process, right? Gauss's algorithm of n equals, I can't remember the formula right now, but n equals n minus 1 divided by 2 or something like this, I think gives you the total. So that's an algorithm that you just plug in numbers and it gives you the solution. And it's proven. There's different ways of solving it. I think it depends on one, what types of problems you're solving classically. What are the limitations there, the time? Because it's either going to be scale, or cost in scale. If it's a large problem, I can't do it because I don't have enough processors. Or it could be time; it takes too long to compute it. Or it could be a combination of both. So when you find a constraint, then just see, well, if I offload the computation to a quantum system, is it running faster? Does it require as much data? Does it require less power, less time? Can I scale it? Can I do something? Can I simulate a molecule at 100 molecules where I can't on classical systems, right? So that's pretty much how in general you want to start with. From there, the timing and everything, that's just more the theoretical, I guess, right? You use a computational analysis at that point.
Great, thank you. Marianne is asking us, how do you decide whether to run using sampler or estimator?
Yep. So that's a good question. So I think it's first is understanding the difference between the two primitives, right? And there's lots of documentation and examples in the Qiskit textbook and many tutorials that you'll see. But ideally, it really depends on how you want to go about solving a problem. If you're going to have parameters and you want to have observables that you need to look and adjust, then estimators only, because by definition, that's what the estimator is, right? You want to estimate your results in that case. Sampler, in a sense, means here's a particular circuit. I want to sample it, meaning I want you to run it 100 times and give me back the results. Let's say, for example, it's a simple circuit like a Hadamard gate. Hadamard gate is going to be set right in the middle. So if I run it 100 times, I'm going to get roughly around 50% 0, 50% 1, and that's it. I don't have to adjust the Hadamard. It's a Hadamard. It's a gate. It's going to give me that result. So I'm going to get a result based on that particular unitary. Now, if I have a rotation gate and I say, okay, I want to apply a Hadamard, but I also want to apply a Z gate after that, and I want to rotate it around phase-wise and see what kind of results I get back because I'm testing for something. Then that's probably where I might use an estimator and just use that particular parameter and say, okay, start it off at pi equals 0, then pi, then try pi over 2, pi over 4, etc. And these are my parameters that I want to adjust because I want to see what the different results get back. Very high brute overview, but there are more details you can definitely look into and figure out.
Great. Myra is asking, why did you use actual system for translation step 2 and actual running on simulator?
Oh, yeah. Okay, so if you want to get the optimizer to optimize against a quantum circuit, you can either define your own quantum circuit. So let's say I could create one. If there's something called, I think it's in the Air library, maybe it's in one of the other libraries. I can't remember which one. You can actually create your own fake hardware. You can say, here's the mapping between the circuits, and here's how it's connected. Here's the errors. You can define all those components. Or you could do what I did, which is you point to an actual device and say, okay, this is the back end. And when I call that optimizer, I just say this is the back end, meaning this is the back end I either have. So the back end equals back end the one that I downloaded or back end the one that I created. And either way, it's gonna as long as it has that information that it uses to optimize, and that's it. So you can use either one, but that's pretty much just to optimize that circuit. When you run on a simulator, I did it for simulator just for speed, because if we run an actual device, we're going to be in a queue. It's going to take a while before our circuit gets to run, and when it runs, we'll get back results. But then it might take a while. So I just did it for speed in this sense here. But if you want to run an actual device, you can actually run it. Pick the actual device you're going to run it on, simulate, and then when you do it, you see in session, when you do backend equals backend, it'll just point to the actual lab backend and not the simulator.
Great. And just the last two questions, which we can, I guess, combine into one from Josh.
Yep.
Qubits Lab, is it suitable for university students to start with quantum computing? I guess that's probably a big yes.
Mm-hmm,
and the second question, does quantum computing support real-time error correction for dynamic optimization problems?
Yes, Qubits, I highly recommend. I use it. In fact, I'm going to be teaching courses next semester, and I'll be using Qubits across the board. So highly recommend it. It's very good. They got a lot of access to different hardware besides IBM as well, and a great platform. Does Qubits support a real-time error correction? Yes. So real-time error correction, don't know what you mean by that. Error correction is something that there's some misnomers on it. You have error suppression, error mitigation, and error correction. Sometimes everything's bubbled into error correction because that's just what we use mostly. But right now you have, as you saw in the tutorials, there's error mitigation, error suppression, there's error identification, these sort of things. So for dynamic optimization problems, when you do the optimizer, that's step 2, optimizer circuit, that's where that optimization level equals X, 1, 2, or 3, or 0. That's where you can kind of blend that in, because when you pick that optimization level, it has those error correction, error mitigation, error suppression techniques built in. If you have your own, you can create your own and use those as well. So the adjustment and the variations of them are open to you.
To actually be able to work in quantum computing field, especially in the next 5 to 10 years, it's important to know at least the basics of quantum mechanics, even for programmers. So
Absolutely.
I would highly recommend that as well. Thank you so much, everyone, for joining us today. It's been fantastic. Thank you, Robert. And hopefully we'll see you guys next time in a month with a different presenter, different topic, but it will be just as exciting. Thank you so much and have a good day. Bye-bye.
Thank you. Well, bye bye.